Now our data is here again. I've recopied it. And our model, based on what we did, is 0.07 t squared plus 28. Y equals 0.07 t squared plus 28. The question is, if we use these values of t and plug them into the model, do we get the same numbers that we got when we observed? Well, our observations weren't completely accurate. We expect some fluctuation between what we observed and what really happened. So we don't expect that these numbers will completely match these. We don't really know whether to expect that this model should really be quadratic. Was the distance really a quadratic function of time? Physics predicts that it would be, but there are some anomalies in the system. Also, the times were done by my counting. 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, okay? And that's not completely accurate. Maybe I was speeding up, maybe I was slowing down. There are all kinds of things that can cause these predictions to differ from what happened. Now, that being said, these are the predictions of the model. I plug t equals 1 into this model, and I get, well, 28.07, and these numbers are all rounded to the nearest whole number. Plug in t equals 4. 4 squared is 16.07 times 16 is 1.12, so we get 29.12 if I did that arithmetic, but it rounds off to 29. Plug in 20, that's easy. 20 squared is 400. Now, 0.07 to 400 is 48. No, wait. 0.07 times 400 is 28. I'm sorry. 28 and 28 gives us the 56. Okay? So if these times are plugged into this model to the nearest whole number, these will be what the model gives you for the y values. Clearly, those values differ, and they differ in kind of a systematic way. Here I've written the residuals. Okay, residuals are just the y value minus the value of the prediction. Okay, so if the y value is bigger than the prediction, and actually it's the prediction minus the y value, we get -1 here, prediction minus y value is -3 here, -5, and so forth. These numbers indicate that the data are higher than the curve, and to the greater extent, they're higher kind of in the middle. So we have kind of this shape of the curve as opposed to these data points. The curve starts out pretty close and ends up pretty close to the data points, but it kind of dips down a little more in the middle. It curves a little more in the middle than the data. So we have residuals here, we have the quadratic curve here, we have the data points here, and there's a picture of how well this model fits the reality. So, a couple of leading questions, and I don't expect most people are going to come up with really profound insights on this, but it's worth thinking about. Is there any evidence that my count might have sped up or slowed down, assuming the actual distance versus time is really, I said linear, quadratic? So you might give that question a little bit of thought. In any case, here we have our comparison between the model and the reality. And the one thing I want you to take away is just how we did this. We got the model, we did the predictions, and we looked at how the model differs from the predictions. Rather, how the model differs from the observations.